Hi, YC. My name is Gia. So today, the most technically impressive thing that I've built that I want to talk about and do a demo of is what I call the abductive scientist. So part of my thesis research, I wanted to explore how a neurosymbolic system um, is able to be sort of an artificial intelligence that combines the strengths of both a symbolic AI that does formal reasoning really well and then also a connectionist neural network that does learning from experience and training data sets really well. So I did some research over the summer at the University of California at Berkeley in neuroscience, and I wanted to do abductive reasoning on those problems. So in my free time, what I did is build out the neurosymbolic system itself. So just gonna set this up. And the neurosymbolic system is supposed to sort of do abductive reasoning over these sorts of problems that I want to talk about today. It's probably the most technically impressive thing that I've built because I find it to be the most interesting. Um, let's see. Okay, so let's do why. Okay, so I chose to run everything in the terminal to show you what's actually happening here step by step, and so you can see the reasoning chains, which is really the highlight of this program. And also the score outputs in real time, which a GUI would have abstracted away. So we start with user input for this, and the demo is this idea that you can put in a category of neuroscientific problems that you want to look at an explanation for. So the first one I'm going to pick is just cognitive neuroscience, and then the specific subfield I'm interested in is attention. So I'm going to click one. And then I want to refine my search query for what goes into ultimately PubMed, which is I am using the API in the system to design this. So I'm interested in plasticity. And then the final query that comes out there is cognitive neuroscience and attention and plasticity. And the and keywords is ultimately what develops is what the query that gets put into PubMed that gives you and returns these search results for what are to be related papers. Um, so the idea is that the first thing that comes out of this is that it fetches these five papers from PubMed, the most commonly cited ones, and you get papers 1 through 5, all of which come with their abstracts. Now, the reason that the abstract is important to come with it is because I use natural language processing to then extract observations that the paper is making. So it does these observations, it comes out with those, and then it highlights the top related concepts, the top related facts that it extracts from those. It appends those facts into the data set that I'm using. Um, in the case that it doesn't already exist, and if it already exists, then that's perfectly fine. And it exists because I've already done this one before. And then it's sort of performing symbolic reasoning now over what has already been done by the neural network. So once it does the symbolic reasoning over the chain, what it does is that you have a semantic score that I designed as a custom one to identify what would be the criteria for the best explanation in this case. And then it gets converted back into natural language because it's following scientific rules now. So you get, because scientific overactivity, it may lead to excitotoxicity, and then it's sort of following the symbolic chain of reasoning to ultimately get you to what a conclusion is in scientific problem solving, specifically in neuroscience. So the conclusion being, therefore, the observed issue may ultimately be due to synaptic overactivity. And the idea here is that when you have a symbolic model and a neural model, you get reasoning that is much more cohesive and also much more accurate in terms of a criteria for an explanation. Ultimately, what it comes out with is also this visual model because I'm using Network X to visually represent it. Um, and lastly, I want to show you the coolest parts of the code. In the reasoning engine is the symbolic reasoner, and I use a recursive function um, in use a recursive function. Let's see where it is. So here's self, trace explanation, and then it goes back into its own reasoning process and does it sort of each call finds a rule that could explain the current target, and then it chains backward until that depth limit is reached. And the next one is the semantic scoring. So get related concepts in the embedding engine, which is the neural part of it. It's a custom scoring function that I have here uh, so that I get a score from both aspects of it. And then ultimately, I have a reasoning model that does semantic reasoning over it. So yeah, that I hope that makes sense.